This section discusses the life of Johann Kepler. Kepler was a German mathematician, astronomer, astrologer. He worked for Tycho Brahe from 1600 to 1612. He published the Astronomia Nova in 1609. Kepler calculated approximations of Mars's orbit using the methods of Ptolemy and eventually creating a model that generally agreed with Tycho's observations to within 2 arc minutes, which was well within the measurement error. In early 1605, he used an ellipse to model the orbit of Mars with much better results, and from this he developed his laws of planetary motion. This lecture will only discuss the laws of planetary motion, but Kepler made a vast number of other contributions to the field of science, including the 1/d squared law of the inverse proportional to the square distance law of brightnesses of light, and also some modifications to telescopes. So what's an ellipse? Ellipse has a size described by its semi-major axis, that's the long axis, and the shape that's determined by the semi-minor axis, that's the short axis going through the center. Kepler's first law stated that planetary orbits are ellipses. Each ellipse has 2 foci, and the sun is at one focus of the planet's elliptical orbit. Showing some Pearson graphics. On the left, showing you how to construct an ellipse. You have a string between 2 thumbtacks, and the string will keep a constant length from the locus or the set of points that form the ellipse and the 2 thumbtacks. The semi-major axis is half of the whole major axis, which spans the entire long side of the ellipse. The thumbtacks mark the foci, or each focus of the ellipse. The sun is at one of the ellipse's foci. Then we have this property called eccentricity, such that you see the distance of the semi-major axis is, the whole major axis, if its value is a, then the distance from the perihelion point, where the planet is closest to the sun, is a times 1 minus the eccentricity, where the distance of the planet when it's farthest from the sun is a times 1 plus the eccentricity. And that's the planet's orbit there. So the critical points are the sun is at a focus. We need to know the major axis size and how the semi-major axis is defined. It's half of the major axis. We need to know the perihelion point. It's the point closest to the sun. And the aphelion point, it's the point with the greatest distance from the sun. Now, the best way to figure all these things out is to use the UNL interactives. Each orbit has a shape as well as a size, and that eccentricity describes the shape. That is how elongated the ellipse is and how far the foci are separated. A circle is an ellipse with 0 eccentricity. In this case, both thumbtacks would be on top of each other. Most planetary orbits are very close to circular, which is why Ptolemy's system worked for so long. The slight deviations from circular are why we need Kepler's orbit. Kepler's second law is that planets sweep out equal areas in equal times. Here, the dots between the area in red, blue, and green are all the same in time. So the time between the 2 red positions is the same as the time between the 2 green positions. Kepler's second law said it sweeps out equal areas in equal times. Well, what does that mean? It means that a planet will go fastest when it's near perihelion, when it's closest to the sun, and it will go slowest when it's farthest from the sun at aphelion. Kepler's third law says that the distant planets take longer to orbit the sun. Distant planets travel at slower speeds. From this, he was able to get a relationship. The square of the period is proportional to the cube of the semi-major axis. Here, where we use proportional reasoning, we measure the orbital semi-major axis in terms of astronomical units, the distance from the Earth to the Sun, and the period in Earth years. That's the distance for the Earth to go around the Sun. So we find that the ratio for any planet in the solar system, the ratio of the square of its period in astronomical units to its semi-major axis in astronomical units to its orbital period in Earth years cubed is roughly 1. Kepler never knew the dimensions of the solar system. He didn't have a way of knowing the exact Earth to Sun distance. Its actual length is measured, or can be measured, by bouncing radar signals off of Venus and measuring the transit time. So in summary, Kepler's laws describe planetary orbits. The planetary orbits are ellipses. The planets sweep out equal areas in their orbits in equal times, and the larger the orbit of the planet, the longer the orbital period of the planet.